Good afternoon. I hope everyone doing well so far. One of the things which I'm quite lucky actually today was that Thomas was actually done everything I wanted to do. And everything I'm going to refer to now, it will be Thomas' paper. So please refer to his paper for most of the application which I'm going through it anyway. Today I'm going through the modeling and computed simulation of aerodynamic interaction in high-rise lift system. This work has been done between the two groups between Northampton University and ThyssenKrupp, which was involved myself, Professor Stefan Kaczmarczyk, Nathan Tongs, Hayder, Peter Feldhusen, Delk, Keith Anderson, and Dudde. At the beginning, let's have a look at the agenda for today. We will look at introductions, multi-body system and fluid and structure interaction model, which is include the airflow-induced vibration and noise, modeling and methodology of that part. And later on, we will have a computer simulation test and result. And hopefully, I will try to finish on time. We get to the conclusion at the end. Based on what Thomas was saying, I'm going to refer to Thomas. Where are you? I can see you. He's probably left. Most of what was based on what Thomas was saying, that the comfort zone of every elevator for the noise will be related to the rail guards, aerodynamic part of it, and the airflow himself too. And these will be the three main parameters which will be causing the vibration and disturbing the ride quality of elevator and lift driving side too. For the multi-body system, the methodology will be that it depends on the discrete or continuous components, which will be including the geometry, mass, stiffness, dampings, various modes of the motions, and constraint on the boundaries, which can be solved based on the stationary or non-stationary, linear or nonlinear, or be in coupled scenarios too. And that can be solved by the Newton's second Hamilton, or Hamilton principle, or Lagrangian equations, and can be included all of the differential equation systems, which will be part of it. And of course, numerical or approximate analysis method to solve the model himself. I am not going through that much equation, and this is the only equation you will see in my presentation anyway. Basically, we will have two different scenarios on this side of it. One will be the structural mechanics, which will be based on the Lagrangian equations. And the second one will be the fluid model, which will be based on the Navier-Stokes equation. In traditional ways, what we have is that people are either dealing with the multi-body dynamic part, 20, 25 years experience on that side of it, or the final element section of it, or the aerodynamic part of it. The reason that this study came up was that we wanted to combine and couple all the three areas into one simulation and have it as much as possible close to the industry, into the actual working prototype himself. That would be one of the main aims of this project. It was in the beginning. But we need to actually have some assumptions. 7,000 degrees of the freedom, it was a bit too much for us to start with. So actually, we started to actually reduce some of the assumptions on site too. So one of the assumptions would be that the elastic deformation of the car and the frame are not accounted for. The top shroud and the bottom shroud will be modeled at the elastic members of the structure, and flow himself will be counted as a non-compressible, single-phase, turbulent, and fully developed flow himself. And the shaft length will be about 105 meters in total. And we were giving about 30 meter length for the fully developed flow at the end side too. Now, what's the fluid and structure interaction? If I want to bring the whole thing, you can read through this one, but if you want to really understand the fluid structure interaction, think about your cars. Most of the time, the MIRA is one of the organizations for automotive industry. They are testing the crash test, and the crash test would be that, for example, on the side, the crash test would taking place on your fuel tank. And the fuel tank is starting to slosh on the side of it around, and that will be default, the shape of your fuel tank himself. That will be the main or a very basic definition of the fluid structure interaction himself. And that could be based on the Newtonian fluid flow model himself, or fluid flow side of it too, or it can be solved by the Lagrangian formulation based on the structure, and arbitrary Lagrangian Eulerlium for the fluid region himself. These are the two main areas that can actually be solved for the fluid structure interaction himself. If we want to start the actual model himself, we have the model of the elevator, which will be importing this one through our CAD models. And we have the profile of the speed, by the jerk above 2.4 and the acceleration of a 1.2 meter per square second and maximum speed rate of the constant of a 10 meter per second for the overall travel of a 30.2 seconds. We use variety of the coding, modeling, and different software to be able to adjust it, because one of the most important and one of the hardest points for my experience was small components inside the actual elevator and lift model himself. And to do that one, I needed to actually simplify quite meshing elements and go into a very small element size to actually be able to actually justify them into our software himself. But some of the basics parameters which we use for this case study was based on the car mass of the 1,000 kilogram, the frame mass of about 400 kilograms, mass per unit of the length of the 0.6 kilogram per meter, or area of the effectiveness of 69 millimeters square. A stiffness of cable will be using as a 7.82 kilonewton per meter. A stiffness of springs for a different position, because all of these ones will be connected by the spring and damper of 29 kilonewton per meter, and damping coefficients will be using as a 20 kilonewton seconds per meter himself. The simulations source that we actually have in the car, this is one of the simulations which is showing the velocity around the shroud himself, and inside the shroud we see that there will be exit point for the cable position, so the air can actually go inside and will be trapped in here. And also we have the exiting cable position, which is again the air can actually travel inside, and you can see it in the bigger picture on the side of it too, both of them too. And the whole thing is starting with the laminar flow at the beginning and ending up with the turbulent side at the end side too. So if I just try one more time, run this one for your, without me talking, it should show the highest position of the velocity which can reach inside of the shroud into 2.2 meter per second. The same thing will be happening at the bottom side at the highest position. We also added the deformation of the top shroud into our simulations too. So while that the whole travel side as a constant speed will be 10 meters per second, we have on side of the elevator up to about 54.4 meters per second, which has been increased massively. But also we can actually measure the pressure on the top shroud and affecting the stress on top shroud too. So one more time. And the pressure on the shroud himself can actually reach up to about 62 kilo Pascal himself. And it's reached the maximum and constant, and then now it's settling down the whole thing. And I have to mention the whole system is vibrating at the same time. It might not be very clear in these pictures, but the whole system is actually having some vibration due to the rail guide system or the excitation of the flow himself too. And that's exactly the same thing on the effective of stress on the shroud. The flow inside the shroud himself, the car is vibrating vertically only. I needed to actually make an assumption that the car is only traveling in the 2 dimensions, so I ignored the Z directions. So the car is only moving up or in the X direction, not the Z one. So I have to make that one as a simplification for myself, make it slightly easier to run the simulation time too. And similar things is happening at the bottom of shroud too. So we have the shroud at the bottom, the deformations and the pressure, and the air travel or the jet engine nozzle effect at the bottom side too is quite clear and taking this. And this one is reaching up to about 6.2, at the top about 6.7 roughly, at the bottom it will be about 6.2. And this is the stream version of it. This is the position of the car actually exists. So the car will be inside. I just wanted to show the stream line is taking place into our simulations, and we can clearly see the effect of a turbulence after that one. This will be the around the car, and this will be at the bottom of the car himself. I think it will be worth to mention this one more time. So we have the traveling coming down. That goes around the system, very nice and clear, up to about 54 meters per second on the side. And then exit positions, which is the turbulence will be clear on the side. And that again reaches to the 54 until it reaches the settle down positions at the end anyway. And finally, it will be the whole scenario We have the top laminar situation, which is started from as a 0 velocity, reach to the maximum of 10 meters per second, which will be this area at the top position. If I go back one more time, then we should be able to see the middle section, which would the car exist in here, and that would be the two different sides of it, which is quite clear the effectiveness of the stress and the velocity, which is it's serving the right quality of the car himself. And finally, at the bottom side, which will be this position of the shaft himself, that the turbulence exists and the airflow or the jet nozzle will be having the effect if another car would try to travel upward. One of other preliminary results and simulation which we are doing at the moment will be a transient scenario of the two cars traveling or passing each other. And that will be another aspect that we will be adding this one, hopefully for next symposium. And hopefully we will add also on the same side the effect of the noise into our system too. So we have a two cars or two counterweights is actually traveling from each other, one going up, the other one is going down, and a turbulence and an effect of each one to each other, not just the multi-biodynamic, not just the FEA, not just the CFD, all three of them together, we will have this one as a part of the study for ourselves too. And I'm on time. Finally, in the conclusion, the feasibility study of developing a computer simulation software platform to combine the multi-biodynamic, the final element, and the CFD techniques for prediction vibration response in arising high-speed and high-rise lifting system has been done, and it was absolutely successful. The work that we've done in here, obviously, we needed to actually simulate it and conduct it from the different and long-time simulation. And one of the questions which we were asking a few minutes ago was for the time simulation. We actually struggled on that part ourselves a lot. We actually managed to, well, actually, we actually done quite well on that one. We managed to reduce the time from 1,000 hours simulation to 150 hours simulation, which for us was absolutely fantastic because we were actually dealing with about 100-meter travel lights. Now think about we deal that one for 400 meter or 1 kilometer height. That would be quite massive actually. So that would be one of the aspects that we actually dealt with that one, and we managed to optimize quite techniques in the coding version to reduce the time for the simulation by the adaptive meshing system or adding import or export system to actually be able to reduce the time of that one. And of course, we are actually having further work needs to be done for the transient position of the two cars traveling each other, adding the noise on top of the system, and making the system more and more complicated to be close as possible to what the industry have or one of the tests, and validating the model performances and full integration of possible excitation source into simulation platform. Thank you so much.